Okay, let's dive into this. You know, it's funny how some of the biggest, most important ideas in science are kind of hiding in plain sight. Today, we're going to tackle one of the most famous of all, Archimedes' principle. And the key to unlocking it is something you've probably done dozens of times without even thinking about.
I mean, really think about it. The second you step into a swimming pool or even just a full bathtub, what happens? The water level goes up. It's so common we just accept it, but why? Why does that happen? And what in the world does it have to do with floating? Well, that simple observation, that's our first clue.
Because the water that you're pushing out of the way, what scientists call displaced water, it isn't just getting out of your way. No, it's actually pushing back. And inside that simple push is a powerful secret, a force that explains everything from why you feel lighter in the water to how a gigantic steel ship can float on the ocean. So first up, the splash and the secret. We're going to uncover that hidden force that's at work right there in the water. That upward push, it has a name, the buoyant force. And honestly, this is the hero of our story today. Every single time you get in the water, this force is working against gravity, lifting you up, making you feel lighter. It's this constant, invisible support that any fluid gives to an object that's inside of it. So, how do we actually measure this buoyant force? How strong is it? Well, that brings us right to our next section, Archimedes' big idea. And yeah, this is the legendary eureka moment you've probably heard about. And the beauty of this whole thing is just how simple it is. What Archimedes figured out was that the strength of that upward push, that buoyant force, is exactly equal to the weight of the water you just pushed aside. So if your body displaces, say, 50 pounds of water, that water is pushing back up on you with 50 pounds of force. It's a perfect, totally balanced exchange. Which leads us to the next logical question, right? The deciding factor, float or sink. As you'll see, it all comes down to a really simple tug of war. So picture this. It really is just a battle between two forces. On one side, you've got the object's own weight, gravity, pulling it down. On the other side, you've got that buoyant force pushing it up. And the rule is simple. If the upward push is stronger than the downward pull, it floats. If the object's own weight wins out, it sinks. That's it. The winner of that little tug of war decides everything. Now here's where this principle gets really, really cool. It's not just for us in the pool or, for rubber ducks. In our next section, From Ships to the Sky, we're going to see how this applies to things that seem way too heavy to ever float. And here's the secret to all of it. The real key is hidden in the definition we just saw. Archimedes was careful. He didn't just say liquid, he said fluid. Now, in science, a fluid isn't just something that's wet. It's any substance that can flow. And that includes both liquids and gases. And that one little word, well, it changes everything. This is exactly how a ship made of thousands of tons of steel floats. It has nothing to do with the steel itself, it's all about the ship's shape. That giant hollow hull pushes aside an enormous volume of water. The weight of all that displaced water is just immense, and it creates a buoyant force that's powerful enough to hold up the entire weight of the ship. And get this, the exact same principle works in the sky. A hot air balloon is basically an airship. When you heat the air inside, you make it less dense, which means it's lighter than all the cooler air surrounding it. So the balloon rises because it's displacing a huge volume of that heavier, cooler air. The weight of the air it pushes aside is greater than the weight of the balloon itself. It's literally floating on air. So the bottom line, the most crucial point is this. Whether you're a massive ship on the ocean or a balloon in the sky, floating just comes down to one simple thing. You have to push aside a weight of fluid, liquid or gas, that is greater than your own weight. That's the whole principle right there. And that leaves us with a fun little thought to chew on. This whole principle depends entirely on displacing a fluid. But the moon, it has virtually no atmosphere. There's no fluid to displace. So if you can't push any fluid out of the way, what does that mean for the buoyant force? What would it even take to float up there? Something to think